So as the tradition goes, this is the mental break time. Of course, you have lectures as lecture 2A, 2B and so on. So anytime you want to take a physical break, right, you can just take a break at that time. Those of you who have been with me again, if some of the jokes are repeated, then that is it. So now we are in your class. It is an elective class. Within 1 semester or 2 semesters, the people are going to pass out and so on. So an engineer, one of you maybe, right? He has finished his degree, he has got a job, 1 or 2 years and so on, and then he got married. So everybody is excited and this and that. But the thing is that this is a very good student, he has got a very good job, the job is very demanding, he does not get enough time. So the wife, right, he is new and so on, and she said, you see, you don't give us much time together, you are so busy in your job. So suddenly he starts feeling bad and he says that, yes, you are very right. And make sure that this time when the weekend comes, whatever my job responsibility and so on, we will go out, we will relax and we will spend some time together. So both are happy. The weekend comes, they get dressed nicely and so on. They go out and they are roaming around the city and relaxing and so on. And then they go to a coffee shop and say, okay, let's take a break here and enjoy and so on. And they order coffees. And once the coffee comes and he is looking back at the menu again, he suddenly says to his wife, please drink your coffee quickly. She said, what? It is pretty hot. No. Drink your coffee quickly, please. She said, this is so strange. We, after such a long time, we have come to relax and enjoy and spend some time together. Why should I drink it quickly? I will relax and take it slowly. He said, no. Look at the menu. Look at the menu. Hot coffee, 1 real. Cold coffee, 2 reals. Joke is over. Okay. So we are back here. We were telling you that fracture toughness, right? The new definition of fracture toughness according to the equation that we showed you is the property K1C, and megapascal root meter units or KSI root inch units for different alloys. We can find it experimentally. So we don't know yet how to find it experimentally. We don't know yet. If we do a stress strain graph, then the area under the graph is a rough estimate of the fracture toughness. If we do an impact toughness, then the impact toughness of the material is there, but this has a unit of energy called CVN, Sharpie V-notch energy. But this is a new something. But if the material has been experimentally tested to find the true value of fracture toughness, then this true value is called K1C. So therefore, the automatic question, measuring fracture toughness, right? Measuring fracture toughness. Now, remind me of this equation later. I want to show you the diagram first. But remind me of this equation later again, that this equation is an important equation. But we will first go and show you the next page, and then hopefully we will come back to this. So now here is the standard fracture mechanics test. It is a sample. If you see, it is a sample somewhat like the impact toughness sample. In what sense? It is a rectangular or a square sample, and there is a V notch cut into it. So in this sense, if you remember the impact test IZOD or Sharpie samples, it is a flat sample. It is roughly a square in cross section, but it is long, and in the middle there is a V notch cut into it. Here the width of the material, compared, right? This is the width, this is the thickness, and this is the height or length. So if you see that the width and the thickness are much more in comparison with the length as compared to the Sharpie. Sharpie was much longer. So the thickness was smaller compared to the height. Here the thickness has quite some value compared to the height of the material. This is the difference. And then yes, there is a V notch cut into it, and here there are places where you will hold the material into the machine. Then you will not take it, we will not take it to an impact testing machine. You will not take it to a tensile testing machine. You will take it to a fatigue testing machine. So you will load this sample under fatigue. Load will increase, decrease, increase, decrease, increase, decrease. Fatigue cycles will be there. And you will load the sample into that machine, which is a fatigue testing machine, and you will load it until it fractures, right? So it will be sort of a fatigue test, but with a very different sample, not like a normal fatigue sample. Okay, so we should now, this you understand, right? That fracture toughness test using compact type specimen and plane strain conditions, specimen dimensions are given, actual test at the actual critical fracture surface is there, and so on. So we have shown you this. We will now get back to the previous page and show how it works. So fracture toughness measurement using compact type specimen. A notch is machined in a specimen of sufficient thickness B. Okay. Now before we go, just this plane strain, don't read anything else now. Concentrate on plane strain. Remember, in your short homework 1, we asked you to give the definition of plane stress and plane strain. First of all, let me say sorry. This is PLANE, my typing error. This plane means simple. Somebody is complicated, somebody is very plain. So this is that simple. PLANE is a flat plane, a 2D flat plane. So PLANE, plane strain, not this one, right? Okay, so now this is there. And plane stress. So if you remember the definition, there are 3 stresses always in X, Y, Z directions. So if any of the stress components, any one of the stress components is so small compared to the other 2 that you can neglect it, then you can say that stress in any one direction is negligibly small or almost zero. So the 3D problem becomes a 2D problem. So therefore, if that happens, then you call it plane stress, that the stress is applied only in one plane, not the third direction. Similarly, plane strain, that there are 3 strains in the X, Y, and Z directions. So if any one of these strains is negligibly small compared to the other 2, then we can call it a plane strain case. Remember, in any real world situation, all the 3 stresses will be there. None of these stresses will be exactly 0. All the 3 strains will always be there. None of them will be exactly 0. We are just saying a very nice term, negligibly small, that compared to the other 2 strains, if one of these strains is very small, then you can neglect it, and the total error that you do in all the mechanics solutions will be, say, 1%, 2% only. Then you can neglect it and you are still 98, 99% right? So the third strain is not 0, it is negligibly small. Now tell me practically, when will this be true? When will this be true? Try to find out, remember in your mind the sample that you do in a tensile test sample. You have a flat plate, you cut a dumbbell shape from it. So it is a long sample with very small thickness and a small width, and in the middle there is a dumbbell shape, right? And this is it. If you take a round bar, then again the diameter of the bar is much smaller compared to the length, isn't it? And then you cut it in the dumbbell shape. So in both of these, whether it is a round bar or a flat bar, if it is a tensile sample, then the thickness of the material is very small compared to the length. So once you do this, you will find the strain, right? A stress and a strain in the axial length direction. And then you know the Poisson's ratio of the material, So you multiply the longitudinal axial strain by the Poisson's ratio and you find the strain in the Y and the Z direction. And all of them will have quite a good value. You do any tensile test and you will see that the axial strain, if the axial strain is suppose 0.3 and the Poisson's ratio of the material is 0.3, then 0.3 into 0.3 will be 0.09. It will not be 0. It will not be 0.001. But now just think that you have a tensile sample, flat tensile sample, but you say, now I take a plate of a much bigger thickness. So what will happen to the strain? What is the strain? A strain is the change in dimension upon the original dimension. So there is a small change in dimension. But in the original sample, when the thickness was very small, you divided this change in dimension by a very small number. So the total number was large. But if the thickness is large, a small change has happened in the thickness and you divide it by a very big number. So the total strain becomes very, very small. So if the thickness of the sample is large, then a strain in the thickness direction will be very small compared to the other longitudinal strain. And if it is very small, you can neglect it. So I am telling you, or you are telling me, that practically plane strain can be there if the thickness is large. So if you remember that diagram, B in that diagram was the thickness of the sample. So if this is K1C, the plane strain fracture toughness of the material, this is yield strength of the material, take this ratio, square it, multiply it by 2.5. So if the thickness of the material is equal to or larger than this amount, then plane strain condition will be satisfied. To find the fracture toughness of the material, this condition is necessary. If you have a sample of thickness which is less than this amount, then you are doing the whole test. You are cutting that sample, you are placing it in the fatigue machine, it has fractured ultimately, but the K1 value that you get is not the real K1C. Okay? So this is it, right? So this specimen with thickness B is a specimen tested and so on, right? So this K1C is a very critical material property, and this is now the proper definition, right? K1C is equal to Y sigma F root pi AC or AF, right? And if you now know this machine, and if you have the proper correctly cut small compact sample and you load it under fatigue properly. Unfortunately, in our College of Engineering, we do not have the fatigue testing setup to find the true fracture toughness like this. So we will take it from tables and so on. We can do an impact test, yes, and we can compare that this material has higher toughness than the other material, but not the proper fracture toughness units. We can do the tensile test and find the area under the curve and find the fracture toughness from there. But again, we can just compare materials that this material has a higher toughness compared to that other material, right? But the proper true fracture toughness testing facility we do not have here. So for that, we just go to the or to other books and find the property which is called plane strain fracture toughness of a material.